let us look at estimating mean mu when sigma is unknown. So we already know how to take care of this problem when sigma is unknown when you have a very big sample. Okay, so especially we are looking at the case when the sample size is small. But the theory pretty much goes with even for large n, whether you have a large sample or small sample, the theory goes pretty much the same way. But this is very important, especially if you have a very small sample. Okay, so we need one more additional assumption so to do this thing. So the initial population we were talking about, that must be a normal distribution. So initial population. So in other words, this is the theorem. Okay, so what happened is this. Suppose the initial distribution has a normal distribution with mean mu and the variance sigma square. And if you pull a random sample out of that, say this is your random sample, and we already know that if you figure out the x bar is going to follow a normal distribution with mean mu, the same mean, and the variance is going to be this variance divided by n. So in other words, that this x bar minus mu divided by the square root of that is going to follow a z curve. So this part we already knew. Okay, so now what happened is that, so now we are looking at the case in general where this is unknown. So what happened, this is correct actually. So if you figure out the sample standard deviation, which is s, the minute you replace this sigma value by s, this quantity is not going to follow a z curve anymore. That is what this theorem is going to tell you. So the minute you replace this thing by s, the sample standard deviation, this quantity is going to follow another distribution which is known as the t distribution. So that's why I put here t. Okay, so this quantity will follow a t distribution with degrees of freedom n minus 1, the sample size minus 1. So that is the theorem. So it's a different type of distribution. Okay, so the properties of the t distribution is going to be this way. Just like the z curve, the t distribution is also a symmetric distribution around 0. So in other words, you already know that the z curve is symmetric around 0. But the z curve has a special property. You remember that the z curve pretty much go down to everything is almost like within -3 and +3 z curve, the way we talk about the z table, like pretty much almost there's nothing after below -3 or above +3. So but the t curve is not like that. So the t curve basically, even though it's symmetric around 0, kind of these are known as tails. These tails are going to be little bit larger than the z curve, those tails. Okay, upper tail and the lower tail. This is known as the upper tail, this is the lower tail. So these are little thicker than the z curve tails. Okay, so there are many, the second property, there are many t curves. So in other words, that's why I said that this follow a t distribution with degrees of freedom. It's like that parameter for the t distribution, the sample size -1. Many t curves, say for example, if the degrees of freedom is 5, in other words, technically we are looking at the sample size 6, okay? 6 minus 1, which is 5. If the degrees of freedom is 5, the t curve, this line, the black line, okay, is going to look like that. Okay, so if you're going to compare the t distribution with the degrees of freedom, say for example 20, okay, it's going to follow, this is going to go a little bit lower here. So this the purple line I'm looking at, okay, purple one. So it's going to be a little higher because it has to be symmetric around 0, and at the same time the area underneath that curve has to be 1. So it has to be, if this is a little bit lower here, has to be higher over here. So it's going to go down like that. So in other words, when the degrees of freedom is larger, so it's a little bit more close to the center. Okay? So when the degrees of freedom is getting larger and larger and larger, so eventually, like if you look at the degrees of freedom 30, it's going to go even below that, and it's going to go above that, okay, like that and that. So when the degrees of freedom is getting large and large and large, the curve is going to is getting closer and closer to the z curve. So z curve is the curve that our previous z curve pretty much goes like a minus +3 here, everything goes up to around that, almost nothing there after that, or below -3, like that. Okay, so the degrees of freedom is getting larger and larger. The t curve is getting closer and closer to the z curve. So that's that. In other words, pretty much the z curve is exactly same as the t curve with the degrees of freedom infinity. All right, infinity means that is a very large number. But for all practical purposes, like, if you look at a big number like 50, 60, 70, like that, it's getting closer and closer to that z curve. Okay, so that's what it is. So now, just like the z table, if you take any low-level statistics books, there are like t tables. Okay, so now I'm going to show you how to read the t table to figure out those probabilities or the cutoffs. Okay, reading t tables. This is the t table in your book. You have on page 683. So this is the 683, the t table you have. Usually, by the way, in most books, you have the t table not like this. Okay, not like so in this t table they give the area inside. Okay, so I'll explain this one. But most book, actually this is the only book I have seen the t table like this. Okay, most books use the t table, this kind of t table. Okay, but I'm not going to get into that. But most books, if you look at different books, any different book, most probably you will see the t table like that. Okay, so here, so in this table, okay, so the very first row, this one is a 50, 60, goes like that. So the very first column, this one is the degrees of freedom. Okay, so let me go with that. Okay, so now, so if say for example, if the degrees of freedom is 10, so you need to stay within this row. You cannot look at anywhere else. Okay, so over here, this, if you are dealing with, if you want to coverage 90%, then you need to look at this column. So this is 90%. This one goes with that. Okay, 95% goes with this column. Now, if you want 98 or 99 or 99.9, these values are right there. Okay, so anyway, so suppose you are looking at the t table value. This is the t table. Okay, t distribution. Suppose the degrees of freedom is 10. Let me go with 10. Okay, degrees of freedom 10. Okay, so in other words, so if the degrees of freedom is 10, so I'm looking at this. In other words, this goes with the sample size 11, by the way, n-1. Okay, but I'll come to that. Suppose the degrees of freedom 10. So you need to stay within this row. So you need to stay within this row. So now suppose you want to find the value over here, leaving 0.05 to the right. Suppose that's what you want. So in other words, what you are looking at with this notation, okay, with this notation, so if this is 0.05, you are dealing with this part is 5%, this part is 5%, so this is 5%. So within that, from here to here got to be 90%. So you need to look at this column. Okay, so in that column with the degrees of freedom 10, so this value t.05 is going to be 1.812. You remember that this notation, the area to the right, t.05, area to the right, this part is 0.05, okay? So now if you are interested in the degrees of freedom, say 30, okay, this is with the degrees of freedom 10, okay? If you want the degrees of freedom 30, then you need to look at this row with 90% in the middle. So in that case, instead of getting this, so you are going to get this, all right? So that instead of 1.812, you will get 1.697. So say for example, for the same degrees of freedom, suppose you want to look at 0.025. Okay, so here I'm looking at the degrees of freedom is still 10. Okay, so with this degrees of freedom, so here, so I'm looking at this. Now the leftover part should be 0.05 to this side, so that way 0.05 here, 0.05, so 5% outside. Within that should be 95%, so that way you need to look at this column. So essentially your value is going to be 2.228. all right, so that's how you read that, the T table. Okay, so the one you have in your book. So now suppose, so you can pick any degrees of freedom. Say for example, I wanted to look at the degrees of freedom 1000. So without even looking at it, can you tell me, can you guess these two values? If you had to make a guess. See, remember that this is the degrees of freedom. When that it is getting large and large, the T curve is getting closer and closer to the Z curve. So this is a humongous number. So this has to be very close to the Z table value. So if you look, so pretty much this got to be like with 90%. You remember the Z table value, 1.645. This one Z table value, the 1.96. The two values I told you to memorize, sort of. So look at that. Okay, so this value, so it's going to be with 95, this is going to be 90%, 1.646. Okay, see, it's very close. And this value is 1.962. See, 1.646, 1.646, and so this one is going to be 1.962. Okay, see that? So that's why. So it's very close to that. So in other words, basically what happened is that usually after this 30 value, they're somewhat close to the Z table value. Okay, somewhat close to the Z table value. That's why in the originally, later you will see that in the beginning I told you that the sample size has to be 30. So that's where that 30 is coming from. But later when I try to get the confidence interval in the next slide, I will show you that in the next video. I will show you that that is the case. Okay. So anyway, so that's what it is. Okay. So this is so I will stop here. And in the next slide, I will show you how we are going to use this T table to construct the confidence intervals. Okay, so all right.